Hi guys, welcome to another All You Need to Know video. So in this video we're going to learn all you need to know about diodes to repair stuff. Diodes are a very common component. It's a semiconductor device and it's the most simple of the semiconductor devices to understand. A diode basically passes current in one direction and blocks current in the other direction. The schematic symbol for a diode is this, and it's very easy to understand. The current passes from positive to negative, which you can clearly see from the symbol because it's passing in the direction of the arrow. The arrow can actually be solid like that as well, or it can just be, it's the same thing. Therefore, a diode will actually convert AC into DC. So if we can imagine we have a diode, it only passes current in the direction of the arrow. So if we feed in, this is ground. If we feed into here an AC signal, which is alternating positive and negative, only the positive halves will come out of the diode. The negative halves will be blocked. So he takes an AC signal and it converts it to a DC signal. This property is called rectification. And this brings us to the type of diodes that you will find. Now, there are many specialized types of diodes, such as Zener Diodes, LEDs or light emitting diodes, laser diodes, transient voltage suppressor diodes, TVS diodes. But these are specialized types of diodes. Today, on this video, I'm just going to talk about rectifier diodes. Rectifier diodes effectively do what I'm saying, they're just passing current one way. And within rectifiers, really, you get three types. You get signal diodes, rectifier diodes, as I just mentioned, rectifier diodes, and another type called Schottky. Pronounce this how you like. It's the surname of, I think the guy was Polish. Somebody say Schottky, Schottky. I say Schottky, and there doesn't seem to be any definitive answer to how you pronounce it, unless probably you're of that nationality, you can tell me. Okay, so these are all rectifier diodes, basically, and they all have this property and they're used in this way. The main difference is that the signal diodes are intended to pass very low currents. The rectifier diodes are basically a power device. So these are for passing high currents and often high voltages. The signal diode is just, as I say, for signals, for low voltage signals where there's no amount of current passing. A Schottky diode is a special type of rectifier, and I'm just going to come on to a moment as to what the difference are. So, we know the diode passes current that way. And this way it blocks current. But when it's passing current this way, does it act like a short circuit? Is it just a short circuit in one direction and an open circuit in the other direction? Basically, it isn't. When the diode is passing current this way, it's called forward biased. And when it's not, when it's blocking current, so you're trying to pass current this way but you can't because it's blocked, this is called reverse biased. Okay. And you have to apply a certain amount of voltage across the diode before it will start to conduct. So basically, in a circuit, if for instance there was 12 volts at this end of the diode, on a normal rectifier diode or a signal diode, it will actually drop across it 0.5 volts to 0.7 volts, depending on the diode. 0.6 is an average. So when you pass current through a diode in the forward direction, you lose a bit of the voltage. If there's 12 volts coming in here, on this side there'll be about 11.5 volts, and that'll be going to your load, whatever's drawing the current. to ground. Okay. So this is an important property of diodes. They have a voltage drop. Your signal diodes and your rectifier or power diodes, basically these days are silicon diodes. That's the material they're made from, and they drop 0.6 volts typically. Early diodes, and possibly some specialised diodes for radio frequency circuits you find now, were not made of silicon. They were made of a material called germanium. And they dropped about 0.2 volts, a much lower forward bias voltage to get it to conduct of 0.2. You'll only really come across these on vintage equipment and possibly in some high frequency and radio circuits. Yeah. Out of interest, before germanium we had selenium diodes, which is an old type of semiconductor diode, and you'll probably find this in the equipment from the 50s and earlier, maybe into the 60s and earlier. And previous even to that, we had thermionic diodes. These are what the Americans call tubes and what the Europeans call valves. Yeah, these are a vacuum tube. So that's old technology. And if you're working on vintage stuff, you may come against these. But this is a specialist topic. Today we're just going to talk about these. Okay, so we know our silicon rectifier diode will drop about 0.6 volts. And the silicon signal diode will do the same thing. It just can't supply as much current or handle as much voltage. The germanium, which you may find a 0.2, and the Schottky diode is actually lower. It drops about 0.15 volts or thereabouts forward. It can be as low as sort of 0.12 and as high as about 0.4, but that's a very typical value. So those are the main type of diodes. And the way you know which is which between the Schottky and the other one, the first way, is to take a meter in diode mode and measure the voltage drop. We'll talk about testing a little bit later, and I'll show you exactly how to do that. Diodes have ratings, okay? And the two main ratings are volts and amps. Amps is quite simple. Amps is the current that can flow before the device self-destructs. Well, it gets destroyed, isn't it? Self-destruct. Before you destroy the device, it can only handle up to a certain amount of current. If you pass more current through it, it will burn out. So the amps is quite easy to understand. And this can be from a few milliamps on a signal diode up to hundreds of amps, maybe more on large power devices. But certainly signal diodes will handle milliamps or 100 milliamps or something in that region, 200 milliamps. Rectifier diodes are typically from about 1 amp to sort of 10 amp, and then you get into large power rectifiers which can go up into the hundreds of amps. So that's the ratings you'll find for current. The voltage rating of a diode is actually the reverse voltage it can withstand. So we know, talking back about our diode, if we have like 400 volts on here and we are passing current forward, this is not the actual voltage we're talking about when we're talking about this. What we're talking about is, with an AC signal, how much reverse voltage it can withstand before it breaks down in the opposite direction. Okay, so if you have a 50 volt diode, it will still only drop 0.6 of a volt forwards or 0.15 for a Schottky diode, but you can apply up to 50 volts in the opposite direction before you'll destroy the device. If you have a 400 volt diode, it's 400. 1000 volt device, up to 1000 volts. Typically, rectifier diodes are between 50 and 1000 volts. So those are the main sort of region of voltages you will find. Schottky diodes tend to be lower, 30 volts to 100 maybe, something like that. So that's how you would read the ratings on a diode. To find the ratings, you have to use the part number. So on the diode will be a part number, and you need to look this up for the data sheet. And once you find the data sheet, it will give you the maximum reverse voltage and it will give you the maximum current that that diode can actually provide. Now, you may reasonably think from the information I've just given you that if you have a faulty diode and you replace it with one which has an amp rating equal to the original or more, and it has a voltage rating equal to the original or more, that the replacement diode will work. And to some extent that is true when we're looking at low frequency circuits or DC circuits. Mains rectifiers, where you're taking your mains voltage at 50 Hz or 60 Hz, then yeah, that is true. Where that becomes not true is in high frequency circuits. So you could have, for instance, in a switch mode power supply, very high frequency AC, 50 kilohertz, 100 kilohertz or more, into the hundreds of kilohertz. And then another factor comes into place, and this is called recovery time. The recovery time of the diode. The recovery time basically is how fast this diode can switch on and off. So when you are applying forward bias and turning it on, and then you're applying reverse bias and turning it off, do you think this diode instantly, I mean absolutely instantly, in no time whatsoever, switches between conducting and not conducting? And the answer is no, it doesn't. It takes a finite amount of time for the current to stop flowing. Or when you go this way, for it to block the current, there's a finite amount of time. And that is called the recovery time. And this becomes very important in high frequency power switching circuits, in particular switch mode power supplies, VRMs, DC to DC converters. This becomes very important. You can get silicon rectifier diodes. These are silicon diodes. They're all silicon diodes, even the Schottky, which is a silicon metal junction diode. You can get rectifier diodes that are called fast rectifiers. Often on the port number, it will begin with FR, FR this, FR that, FR 500, FR 150. These are fast rectifiers. These diodes are intended to be used in higher frequency circuits. Schottky diodes are even faster again than fast recovery rectifiers or fast rectifiers. So generally in these type of circuits you will find Schottky diodes. For instance, on the secondary of a switch mode power supply, the rectifier diodes will be Schottky because they need to switch very rapidly between conducting and not conducting. The upshot of all this is that apart from in low frequency and mains frequency circuits, you need to replace the diode with a correct type or with a proper, shall we say, with a proper equivalent, one that's equivalent in the switching speed as well. If you're not sure, I suggest you ask on our Discord server. You can post questions on the YouTube, or you can go to, I always recommend, badcaps.net and join their free forum. It's free, just sign up with an email address, choose a username, and you're in there, and you can ask questions. You can post photos of your circuit and your diode and say this is the part number, what's the equivalent, and you'll find very knowledgeable guys to help you. And I'm sure with experience you'll become very knowledgeable guys, and then you'll be able to help other people. I mean, that's the nature of how this works. So just bear in mind that recovery time is another important factor when it comes to selecting a replacement diode. Just before we leave this sheet of paper, I'll just mention a couple of things for completeness. When you see on a circuit board diodes, they will normally have a part number of D something, like D1, D15, D4900, whatever. This is not the value of the diode or the type, this is just the reference number for that part on the schematic. So you'll often see D this, D that, D the other. That's quite a good way to tell if a component actually is a diode. You'll see others more specialised like ZD, which is a Zener diode, and others, but at the moment we're just talking about diodes, so that's how you recognise them on on the actual silk screen printing, if there is one on your PCB. Just mentioning about old type of diodes, there were also crystal diodes, and another term, old term, cat's whisker, which is a type of crystal diode. These were used in the original radio receivers. So again, it's archaic terminology for archaic components, but just for completeness, I will just mention that those things existed and they still exist in very, very old equipment. Let's just have a talk about where we're likely to find diodes used in circuits. I mean, diodes have many, many uses, but these are a few examples of where you would find diodes in circuits. So a very simple example would be for a device that's powered from a mains power pack, a wall wart, if you like the American term, a power pack. So on this you will have a jack socket with a center pin, and the center pin is usually positive, and then the negative goes to ground, and this is plus 12 volts or 5 volts or whatever the device requires. Now it's quite possible to have a power supply that's wired the other way around with a negative here, so there is a possibility of plugging the power connector in the wrong way round. For this type and similar situations where you could connect something the wrong way round, quite often they'll just put a rectifier diode in here, and then this goes to ground. Yeah. And what happens now is if you put the, and this is your load, this is your actual load circuit, this is the device connecting to ground, okay? And what happens here is if you put a power supply on the wrong way round, well, the diode only conducts one way, so you can't damage the device. So that's a very typical application for diodes. You'll often see that sort of thing. Another quite typical application is where you want to drop a certain amount of voltage. For instance, if you have like the base of 2 transistors and you always want one to be 1.2 volts lower than the other one, which you may, this sort of thing you will find people designing circuits. So often in this type of circuit, they'll have from the base of the first transistor 2 diodes going down to the base of the next transistor, something like this. It's a bit more involved, but this is the principle of it. So what happens now is that if you have a signal coming in here, the same signal comes, well, rectified coming through here. If you have a positive voltage on here, if you have a positive voltage on here, the voltage on here will be 0.6 volts. That's the voltage drop forward, yeah. Plus another 0.6 volts. That's the forward voltage drop of the other diode. The voltage here will be 1.2 volts less than the voltage here. And this is, you'll find this in amplifier circuits and similar devices where you want to put a certain bias voltage onto transistors. So you'll see them used that way, basically, if you like, to drop or regulate the voltage, so one voltage is slower than the other. A couple other good examples. You'll see them used as effectively little logic circuits. So I'll give you a typical example. 2 diodes coming in here to another transistor, yeah. Ground. We'll talk about transistors later. Some sort of load, could whatever the load is, plus volts, yeah. And now, by applying voltage to here, you can switch this device on. By applying voltage to here, you can switch this device on. But if this voltage is 12 volts and this voltage is 5 volts, depending where it's coming from, you don't want the 12 volts to go back into the 5 volt circuit, or even the 5 volts going to the 12 volt circuit. So because these only conduct one way, whatever voltage is here can never get to there, whatever voltage is here can never get back out to there. So that you'll find that type of use for diodes. Another good example of this, motherboards. So you have a Cmos battery. Cmos battery. Plus to ground, yeah? And this powers the I/O chip, the thing that starts the laptop, yeah? Called an SIO chip. And this powers this. And also, you have, when you've got your ATX power supply plugged in, you have a standby voltage, okay? This is your ATX. Okay. The Cmos battery is about 3.3 volts. Okay. And your standby voltage is 5 volts on your power supply. And you want both to power this chip. So when the ATX is switched off, the Cmos is powering it. When the ATX is switched on, it takes over. Again, where you would do this is basically with 2 diodes. Like so, yeah. So when this is off, there's no volts here. So this side's got 3.3 volts, this has got 0 volts, and it conducts that way, losing about 0.6 of a volt. So you get about 2.7, 2.8 volts coming out here. Okay. When this turns on, you've now got 5 volts here, powering here. Yeah. This end is now about 4.5 volts, half a volt's drop. Okay. This diode still has 3.3 volts on this end, but it now has 4.5 volts on this end. So this is higher than this, and it can't conduct, it's reverse biased. So automatically, the SIO chip will power from the ATX and all the battery, but the ATX 5 volts never ever gets into the battery. So that's another good one. And these are common circuits you'll find. I'll just do, another one. So this is quite an interesting circuit. We have, let's say, 12 volts, okay, and we have a circuit with a relay, which is basically an inductor coil and some contacts. It magnetizes them and it pulls the contacts together. And this goes to your load. So we'll power this with a transistor, again, to ground, base. And to turn this on, we put some voltage on the base. So when we put some voltage here through a resistor, this turns on, the relay contacts close, and it switches the load on. This could be your little headlight switch on your car, which can't pass much current through the contacts of the switch. So it switches the transistor, and this switches your headlights relay, which then sends 20 amps or whatever into your headlamps. Yeah. So effectively, it's just switching the headlamps without much current flowing through the switch itself. This type of circuit, you will always see a diode like this connected across the relay. Now, if you've been understanding what I've said to you earlier, this diode cannot conduct in this direction. It's reverse biased. When this transistor is switched on, there's near enough 0 volts here, about 0.2, but there's almost 0 volts here. So this diode has 12 volts on one end and 0.2 volts on the other end, so it can't conduct. When the transistor is switched off, this has got 12 volts on one end, and it's now got 12 volts on the other end, because this is open circuit. So the 12 volts is also here on this end of the coil. Yeah? It's got 12 volts on both sides, and it can't conduct. So what's that diode doing there? Why is it there? Well, the reason this one's here, and you'll find this in lots of circuits with inductors, and it's worth mentioning. When you pull the current through the relay, this inductor builds up a magnetic field, and it stores energy in the magnetic field. When you switch off, and this transistor suddenly switches off, the magnetic field collapses. The relay contacts open, the field collapses. And by doing so, it generates a large positive voltage on here. All the electricity stored in the magnetic field now comes out of the magnetic field. It's got to go somewhere. So it causes a very large voltage spike on this end. It suddenly spikes up. And until this magnetic field completely collapses, and it goes back down to 0 again. So you get a big spike. That spike may well be too much voltage for this transistor to withstand. So in fact, when you switch it off, it blows the transistor because of the spike coming from the coil, the inductor. When you put this diode here, it can't happen, because as soon as you get a spike here, this end goes a higher voltage than this end, and this diode shorts the circuit out through the coil. Shorts the high voltage back into the coil. Yeah? That is called back EMF, and one of the subscribers asked me to talk about it after I did the inductor video. All you need to know about inductors to fix stuff. So that's that one. So there's some typical examples of where you will find diodes in circuits. There are many, many more, but I hope this gives you 4 different reasons that diodes would actually be used. There's one other use of diodes, rectifier diodes, which is so common that I want to explain it to you. And this is a circuit called a bridge rectifier. Now I mentioned previously that a diode effectively turns AC into DC. So if you have an AC signal and you send it through a diode, in the positive half cycle this diode will conduct, and in the negative half cycle it will block the voltage. So coming out through the diode basically is a positive half cycle, then nothing during the negative half cycle, then the next positive half cycle and nothing, and so on. So here you get a pulsed DC signal, and this can then go into your load circuit and back to the other side of the AC. Okay, so this is just AC. Although this works and you're now getting DC from an AC supply, it's not a very efficient way to do it, because half of the time you're not passing any current, you're on the negative half cycle, you're blocking it. So this is where we use a bridge rectifier, and a bridge rectifier is made up from 4 diodes. So I'll just show you how this circuit actually works. So we have 4 diodes coming from the first one here. There's 2 diodes. And I always have to refer myself because I tend to get them the wrong way around. 2 diodes like so. Okay, and coming from the other one again is 2 diodes, one pointing that way to here and one pointing the other way to here. Okay, and this end is the negative end of our load, and this end is the positive end of our load, and the load is there, the device we want to power. This is AC. Now let's have a look at what happens. During the positive half cycle, this pin is positive. This is positive related to this. So this point here is positive in relation to this on the positive half cycle. Okay. Let's see how the current flows through our bridge rectifier. So the positive flows in and it comes to these 2 diodes. So it's got to go one way or the other. It can't go that way because this diode is reversed biased. This end is positive compared to this end. But it can go through this way, forward bias. So the current flows through here, into our load, back out the load, back up into the bridge rectifier, and again it's faced with 2 choices, yeah, when it gets to here. Now you might think, well, it can actually go that way or that way, but in actual fact you'd be wrong. This point is at a higher voltage, this point is a lower voltage than this. This is on the positive half cycle. This has already come through our load. This is the low voltage side. So this point is a higher voltage than this is. This diode is now reversed biased. But where the current can flow is through here, down into the negative. It can't go that way because the polarity is reversed on that diode. Now let's see what happens when this is going negative and this is going positive. I'll do it with a different pen. This end is now positive with respect to this end. So again, the current comes to here, it has 2 choices. It can't go that way because it's reverse biased. It can go this way. So it goes this way, down through our load. Look what's happening. It's going through the load in the same direction. The polarity is the same, yeah? Back up into here, and back up to here, and it now has 2 choices, yeah? This point here is negative in comparison to here, so it can't flow through this diode because this end of the diode is more negative, is reverse biased, yeah? But what you can do is flow through that one and back to here, okay? And that there is your voltage path, one direction, yeah, or the other direction, yeah, sorry, that way. So that is a bridge rectifier. Now what happens here now is here you get first of all the positive half cycle from here, then when this goes negative and this is positive you get the positive half cycle from here, then you get the positive half cycle from here, then you get the positive half cycle from here. So what it's basically done is turned the negative halves upside down. Yeah? And now you're getting all of the waveform effectively coming through. You're just inverting the bottom half of it. And now 100% of the power is coming through rather than 50%. Okay? That is a bridge rectifier. This circuit, you'll sometimes often find this made from 4 diodes. And you'll also often find it in one package marked AC, plus and minus. So it's either encapsulated with 4 diodes or the 4 separate diodes. So that is the last typical application. And you can see now that diodes are used in a number of different ways. And I've shown you a few of them. There are plenty more ways you'll find diodes used. But I'm sure that will teach you enough about diodes to get you started. Now let's have a look at how diodes actually fail. What goes wrong with them? We're not designing circuits, yeah? We're trying to fix stuff. So what goes wrong with them? Well, they can fail basically in 3 ways, but mostly in 2 ways. So one way a diode fails is it goes short circuit. If a diode goes short circuit, it's just a piece of wire. It conducts both ways. It doesn't even drop 0.6 or 0.14 of a volt or whatever it was supposed to do anymore. So diodes can go short circuit. They can also go open circuit. So they just burn out and now they're just completely open circuits and current can flow in neither direction. That is the most common 2 ways they fail. And to be quite honest, both failures are fairly common. You'll find short circuit diodes, you'll find open circuit diodes. And I wouldn't say there's any particular preference between one or the other. It might depend on the type of equipment you're working. You might find in certain types of applications they go short circuit more often than they go open circuit. But if you work on a wide range of equipment, you'll find both. The other way they can fail is that they go leaky. And you'll often find this more with signal diodes, whereby it's not short circuit, but it conducts like a resistor. So it conducts like a diode in one direction, but when you reverse the voltage, it acts like a resistor in the other direction. So it kind of acts like this. Diode with a resistor across it. Yeah. So in the forward direction, it acts like a diode, and the reverse direction is acting like a resistor. So you'll see that as well. Generally in signal diodes. If that happened in a rectifier diode, it'd just burn out. So if that happens in a rectifier diodes, it doesn't happen for very long. I'm talking like milliseconds type of thing, yeah. So that's the way diodes normally fail. So let's now wind up by having a look at some diodes, and let's have a look to see how we can test diodes both in circuit and out of circuit. These are through-hole diodes. We'll look at through-hole first and look at surface mount. These are actually signal diodes. You can probably see the markings. 1N4148 is the part number. In through-hole, anything that starts with 1N, it will be a diode. Yeah, so these are 1N4148s. Very typical signal diodes. The black end is the cathode. That is also referred to, if you like, the bar that's on the arrow. So the arrow end, well, I'll even draw on the thing here. It conducts that way, yeah. And I'll wipe it off after with a bit of isopropyl. So the bar is where you see the bar on the symbol, and that's always the case really with diodes. So that's some very common signal diodes. Let's have a few more rectifier diodes. These are 1N4007. These are very common silicon rectifier diodes. They're a 1 amp diode. Again, the symbol points that way, yeah? So this is the bar. I'll find something to put with this. This is the bar on the symbol, the stripe. These come in, by the way, from like 1N4001, which is a 1 amp 50 volt, up to 1N4007, which is a 1 amp 1000 volt. If you're buying some of these, just buy the 1N4007, and you can use that to replace any of the other types, 4001, 2, 3, 4, 5, or 6. So that's a very typical 1 amp diode. Let's have a look at a few more. As we get into larger currents, we get larger diodes typically. So the higher the current, the bigger they get. These are some 3 amp diodes. Okay, 3 amp diodes. Again, the silver points in the direction, so the bar is on the line on the symbol again. So that's some 3 amp diodes. What else do we have? Yes, we have some Schottky diodes. These are higher powered diodes. So these are actually 10 amp diodes, rated at 60 volts, or at 140 volts another one. So without looking up which one I've got behind, it's one or the other. It's a 10 amp 60 volts, or a 10 amp 140 volts, or 5 amp 140 volts. So look up the part number. When you look at the part number, I'd say probably, after waffling, F5 is probably a 5 amp and Q60 is probably a 60 volt. Likely to be. Now you'll see this as a symbol actually showing you which is the cathode and anode. So that's quite common for Schottky diodes. These are some 100 volt 1 amp diode, no, 100 volt 10 amp diodes. Yeah. And again, if you can just see it, you can probably see the symbol on there. There you go. Again, MBLF10 is probably like it's a 10 amp diode, but you'd have to look at the part number to be sure. So that's that one. We also get, and I'll show you these, it's quite common, diodes like these. So this is actually a diode matrix. This is 2 diodes connected together, and the cathode, the stripe, is in the middle. So anode, cathode, and a pair of diodes called a diode matrix. Often find these where you get 2 in the same package. This would be called common cathode because the 2 cathodes are joined together. You can also find common anode as well, and you'll find similar things in surface mount devices. These are quite common. You'll find them in power supplies. Let's have a look at some bridge rectifiers. So this is a bridge rectifier, encapsulated in 1, not just 4 diodes. So this is marked 8 amp 250 volt. This is your AC coming in, and this is your plus or minus. Okay, so that's a typical one. Let's have a look at another one. So AC on the 2 middle pins, plus and minus. To find the rating of this, you would have to look at the part number, KBU808, and find out what it actually is. We have some more. There's a few more in this bag. Yeah, RS204 different ones. So again, AC are the 2 middle ones, plus and minus. Bridge rectifiers can get quite big. I mean, you can get some really quite large ones. This is a fairly small one, but you see how it's marked. AC, plus and minus. Almost certainly have a part number on it somewhere. Yeah, there you go, part number, so you can see what it actually is. The bridge rectifiers are always, I say always I've ever seen, a silicon diode, so each one drops 0.6 of a volt, not Schottky diodes. Come on, we have a few varieties. You get round ones as well. 2 ACs in the middle, plus or minus. This is a big one. Look at this. It's a bit. I might just be able to focus up there. Just like, there you go. So again, marked AC plus. And I'm guessing the others are marked somewhere. Is there a minus marked on it somewhere? Okay, there isn't. We can use this one to figure out how we will do it with the test meter to find the polarity of a bridge rectifier. Another one, AC plus. And nothing else marked on it, okay? So we can look at that one as well. So those are bridge rectifiers. There's one other type which you may well come across I just want to show you, and then we'll go on to the surface mount ones. I don't physically have one of these to show you, but I can show you a picture one. So this is a high power diode. It's actually 70HF120. It's 70 amp, 1200 volt, high voltage, high power rectifier. And this has a big metal stud on it, and the bolt. These are called stud diodes, so it comes with the variously the washer and the stud and the bolt. Typical that. There's a picture of a hand. I know it's not a very good high-res photo, but that gives you an idea of how big these are. This is quite a large device, and if you do find these in high-power equipment, they'll usually be bolted to a large heat sink. So those are stud diodes, and you might come across that. Now let's have a look at some surface mount diodes. This is a power supply from a TV. So this has, these are through hole, but you can see diodes on here. These four together, this is actually a bridge rectifier made up of 4 discrete diodes rather than an encapsulated device. Over here, if I can just find it, there is a surface mount diode, or one, yeah, that thing there that I've just built into the middle of the shot. So this is a surface mount diode. Again, the black is generally the cathode. Often you'll find diodes that look like, I'll just get to one, yeah, these sort of devices. Now these can be transistors or diodes. This one, 1AM, actually is a transistor, I know that. But you can find diodes in this type of package as well, which is called SO23. Small outline transistor 23, which is 2mm by 3mm. But in actual fact, these can be diodes or even dual diodes in the same package. So you'll find diodes in that type of package as well. Let's have a look at another board. So this is a motherboard, a scrap one. Again, there's lots of devices down here. These could be transistors, they could be diodes, they could even be something else. So often with these type of devices, in fact this WV3, I'm sure that is actually a diode. In fact, I even tell you what that one is. It's a BAT54, because I came across some of these on a faulty board on a video recently. BAT54. And these come in diode networks. Actually, let me just show you on a piece of paper. Actually, these little diodes that look like transistors but could be diodes. So these things. The only really way to find out is to look up the SMD code, the part number, or on the schematic for that matter. But these are very common on motherboards, and I want to just give you a little bit of information how you'll commonly find these. So there's one particular type of diode called BAT54, and it's an SMD diode. I actually have, if I just find a pack of them, I have a whole row of 100 of these diodes. But basically, this diode comes in 4 versions: BAT54, BAT54A, BAT54C, BAT54S. And you might wonder what the difference is, and are these just compatible? Well, actually, no, they're not compatible, and these are so common. I'm going to show you them. These are actually 50 volt, 200 milliamp Schottky diodes. So they have like a low voltage drop of 0.15, and they're very fast switching diodes. But they're effectively signal diodes. They're only, low current, 100 milliamps or something, 200 milliamps. So they all look like this. This is pin 1, 2, and 3, and all of them look the same, but they're not the same. I'll just draw them and I'll show you what these actually are. These are useful to, if you're repairing motherboards, keep these in stock, all of them. Okay, so this one has a diode from here to here. Okay, anode, cathode, and it has a diode in there. This one is the A, and the A is actually common anode. So both, it has 2 diodes, and both diodes have the anodes connected together, and it's like that. Okay, and this is common anode A. C is common cathode, so it's the other way around. So it has 2 diodes in here. Going this way, and this is a common cathode. Both the cathodes are connected together. Remember, the bar is a cathode and the other arrow is the anode. That's the name of the 2 terminals. What's BAT54S? What do you think this is? Again, it looks the same, 3 pins. It has 2 diodes in it. And there's only really one other possibility now, and that is this one. One diode like this, and one diode like this, the other way around, coming to here. And this is serial. serial, common cathode, common anode. My writing's bad, isn't it? It used to be great until we had computers. And it's just a single diode. So that's a very common one. I just thought I'd show you how they are because you'll find them a lot. Often you can tell it's a diode because on the markings on the motherboard it will say something like D101, and if it was a transistor it would say usually Q304 or something. Yeah, Q or D, you can often tell that way. Otherwise I say look up the SMD code and find the part number, or the other way is to look at the schematic or a board view, and the last way is to ask on the forum or ask on our Discord, which is a very nice place. Okay, so we've looked at some diodes and what they look like, and the ones you're most likely to come across. Let's just finally now look at testing some diodes and see how we would test them. By far the easiest way to test diodes is with a multimeter on diode mode, on my meter. I'll wait till it bleeps twice and it's in diode mode. This now isn't measuring resistance. Look, it says VDC. What this actually measures is the forward voltage drop across the diode. So let's take some of the ones we were just looking at and see. So this is the 1N4148 signal diode. The cathode, the bar, the cathode should be the positive. So put the positive lead to the bar and the negative to here. It doesn't conduct, okay? It's reverse biased. Positive cathode is reverse biased. To make it conduct, we want positive to the anode. Now it conducts. And 5, 6, 7 is the forward voltage drop. So you can see it conducts in one direction, it doesn't conduct in the other. And the second thing we can tell, 5, 6, 5, that this is a silicon rectifier diode, because between 0.5 and 0.7 is a silicon diode. Let's have a look at another one. We had a look at some 1N4007s again. So positive to the anode, 0.544. See, it reads the same even though this is a 1 amp diode. Other way, positive to the cathode, it doesn't conduct. So that's a good diode. What else did we just look at? We looked at some 3 amp diodes. So these are 3 amp diodes. Again, positive to the anode, 0.509. So this is again a silicon rectifier. It doesn't conduct the other way. We had a few more, so let's look at the other ones we were actually just looking at. We looked at, I think we looked at this one, F5 and K40, yeah, F5KQ60, which I thought was probably a 60 volt and 5 amp. And there's no way to measure that, but you can see if it's any good, and you can see if it's a Schottky diode. So, positive the cathode doesn't conduct. Go the other way around. Positive the anode. 0.155, you see that's a much lower forward voltage drop. And if you have stayed awake, you'll know that is a Schottky diode. We look at, yeah, we probably look at some more. These were 10 amp diodes. Again, these have a symbol on them. Doesn't conduct that way. It conducts this way. That is a Schottky diode. Yeah, 0.245. A good thing you're telling now. A, you can test the diode. B, you can work out the polarity, because the anode is the one with the positive lead when it conducts. The black is the cathode, yeah? So you can figure out, A, is it any good? B, is it a Schottky or is it a silicon diode? And C, which terminal is which? And you can work all that out with your multimeter. Otherwise, use a components analyzer. But this is the easy way to do it. What else have we got here? We've got some bridge rectifiers. Down here. So you can see this bridge rectifier. I'll just zoom down on it a bit and we can see the terminals. So here's another one, bridge rectifier. We can see on this it's marked AC, AC, plus and minus. Let me show you how a good one should read. So we start with the red lead on one of the AC terminals, and it should conduct to the positive. And we can see the voltage drop, yeah? And the other positive terminal should also conduct. So both of those, when they're positive, should conduct to the positive terminal. But if we put the black one on here, it shouldn't conduct. Yeah? Nothing, nothing. Okay? Now let's go to the other way. So this is your negative terminal. So with a negative, you put the black lead to either of these, it conducts. It's the opposite way around, yeah? Yeah, and in this case, you put the red lead to here and it doesn't conduct. So the red in the middle only goes one way, and the negative in the middle only goes the other way. Yeah? What happens if you measure across the positive and negative? Well, if you measure the way it's marked, so the red to the positive and the black to the negative, it doesn't conduct. But if you measure it the other way, with the red to the negative and the black to positive, you'll see a reading. And effectively that's because you're coming through two diodes in series if you look at the actual schematic for the bridge rectifier, which I just showed you. I can just find this again. Here's one, here's a diagram. So effectively you're reading through two diodes, that's what it comes down to when you see that. But you only see it when it's effectively back to front, yeah? When the red's the positive you don't see anything. So that's that. So we get another one. So again, oh, and also, I forgot to mention, between the two AC, it shouldn't conduct either way. Okay? So let's go for this one. Is it marked? Yeah, I'm sure it's marked. Let's see if we can figure out which pin's which anyway. So there's nothing there. There's nothing there. Let's find the conduction first. Well, that reads, oh, that's reversed across the plus and minus. So we now know this must be plus. It reads nothing, yeah? Right. Is this reading good? Yeah. Okay. So that's conducting, okay? And this one will conduct. So this is the positive end. Okay? As we said from measuring the other thing. If we go to the other one, it doesn't do anything. Now switch them round. So the negative should conduct to this end. Okay? Yeah? Off both the AC. But it shouldn't conduct to this end. Okay? And the two ACs shouldn't conduct at all. Okay, let's use that. We said we were going to identify one of these, didn't we, which isn't marked. It says AC. Yeah? It says AC. So let's see if we can find the other AC. So if we know this is one AC, the other AC will not conduct in either direction. Yeah, it doesn't conduct with it that way round. It doesn't conduct with it this way round. So we know those, if it's a good diode, those are the AC. If this is the positive, this should conduct. Yeah? And then this should be the other AC, and it conducts. We know this is positive. Yeah? So we've got it. That, in that case then, if this is the negative, what happens with here? So we go to here. Positive here shouldn't conduct. Yeah, it shouldn't conduct that way. Go to this one. This is the negative. Put the minus here. Conducts. Conducts. So we know that's good. And if we go across the two AC, either way we know it doesn't conduct at all. And if we go to the plus and minus, with the positive to the plus it should conduct maybe about 900. Yeah. And the other way around it shouldn't conduct. So that's how you test diodes. In many cases you can also test diodes in circuit. At least so far as you can test if they're not short. So we can have a look at a few just in circuit. So here's some diodes. Should conduct. Doesn't conduct, yeah? If it's a short circuit you'll find the short circuit one. But sometimes when you get into lots and lots of these little surface mount diodes, we're looking at things on here which could be diodes, you may have to remove the component to actually know whether or not you've got an open circuit one. Again, a short circuit one you should be able to find. So let's have a quick look down here. Look at some of these, just balance this so we can see it. So that means nothing. And bear in mind some of these might be FETs and some of these might be transistors. Also bear in mind the transistor can look like two diodes. So if you don't know what the component is, you probably can't come to any conclusive answer with these type of things. You need to look up the part number to see what they are and then try to test them. So there you go. You can find short circuit diodes quite easily in circuit, but open circuit diodes quite often you can't find. Sometimes you can test them if they're working, and sometimes you can't. Okay guys, I hope you enjoyed that video. That's plenty of stuff about diodes, but now I think you will know, and you will agree that you know all you need to know about diodes to fix stuff. Okay guys, hope you enjoyed that one. See you all soon on another video. Adios amigos.